Alrighty, our tutorial is plastic injection molding on SOLIDWORKS. The first thing you need to do is add it. So you're going to go to settings here, add-ins, and we're going to go add SOLIDWORKS plastics. So as you can see, it put a little tab here. This is just a simple part we have open here. It's just a symmetrical sheave. And so we're going to go to our SOLIDWORKS Plastics tab. And we're going to come over here to this guy right here, Plastics Manager. Alright, so the first thing we're going to do is create a mesh on this part. Considering it's such a simple part, we're just going to do an automatic mesh. So we're going to go over here to create mesh, mesh type, automatic. Here's some other options. And then we're going to go to create mesh. Alright, here's our mesh. Our next step is to specify our material. So we're going to come over here to material not specified, click settings, and we're going to click this box right here, browse the database. We're just going to do a simple ABS generic material. Let me expand this here. When you click on your material, here's some material properties that you can look at. Just click OK. Our materials now is specified. Click check. Our next step is to specify our injection location. That is under boundary conditions. General rule of thumb is specify your injection location farthest away from your thinnest wall section. So in that case, here's our thinnest wall section, so we're going to specify over here. You can click predict flow pattern if you're interested. Our next step is to specify our clamping force location. So that's also under boundary conditions. You're going to want to specify your clamping force direction normal to your injection location. So in that case, in this specific case, we're going to use our right plane. Alright, now we're just going to do a simple flow analysis. So we're going to right click flow and click run. Alrighty, now that our flow analysis is complete, you can see a results advisor popped up. This results advisor is your friend. It tells you how to change your inputs. So to change the fill time, reposition injection location, etc. This results advisor is definitely your friend. Here's some available results. So first is fill time. With fill time, you can run a little animation here to specify your flow. Or excuse me, not to specify. And in your available results here, you can click through and see these different results. And as you notice, your results advisor jumps to that section. So it's really simple. Next, we're going to show you a poor fill location and the defects that can occur with specifying wrong fill location.
This is showing an adjusted fill location at one of the thinner areas on the part to show some of the more negative results that we could get from a plastic injection molding. We're going to look over here at the results table starting at pressure at end of fill. So this shows a heat map depicting pressure throughout the design part. If the pressure is not geometrically uniform at the end fill, then adjustments need to be made to the injection location. And here we actually have a fairly even pressure throughout the end of the filled part. So that's okay, but we're going to move on to look at the shear stress at the end of the fill. So it's important to note that the max shear stress throughout the fill has to be less than the desired shear stress for your selected material. So the maximum suggested value for the ABS was 0.3 MPa. This is showing a max shear stress in the fill of 0.3 MPa. So this means that there's adjustments that are going to have to be made. One of the ways you could fix this is by changing the injection location to an area of greater part diameter. Okay, we're going to move on to look at volumetric shrinkage at the end of the fill. What this shows is shrinkage distribution as a percent of the designed volume. These higher areas of shrinkage usually occur in thicker regions of the part where there's insufficient packing, and these are areas of high concern where you could be seeing defects. So we see that near the infill location, there's a higher percentage of shrinkage, and also at the outer radial region up here. So this is something we would want to go back and make adjustments to try to limit the possibility of defects in the part. We're also going to look at, very similar to the volumetric shrinkage, is the sink marks results. So what this is showing is these are just more defects that are due to insufficient packing. So as you can see, there is greater possibility of this happening in this part around the outside region, the kind of the outer radial section, which is because that's most likely kind of getting filled last, and there's there might not be enough pressure in the fill to fill out to these parts. Okay, we're also here, I'm going to look at the weld lines results. What this shows is where flow from different sections of the parts meet, and it's important to try to limit these interactions because where the flow meets, you can have buildups of air bubbles pocketing up, and that is also showed in the air traps function, which kind of shows where these pockets or bubbles of air can build up from excess being left in the part from not being able to escape the mold. And these are areas where you can have more defects, and they need to be accounted for. Cool. Yep.
Okay, now we're going to look at a part with some more complex geometry. We're going to take a look at some of the other features of SOLIDWORKS plastics. We're going to start with a new study, and our first big change is going to be here with the mesh. So firstly, instead of going to automatic mesh, we're going to start with a tetrahedral hybrid. Now, really the difference between these three are accuracy of the flow, and when you're choosing between hexahedral and tetrahedral, the only real difference there is computational expense and how long the simulation will take to run. So we're going to start with the tetrahedral. That's good for most geometries. We're going to go ahead and create that mesh. First option up here is the coarse or the fineness of the mesh. So if you increase that to fine, it's going to increase the number of nodes and also the computational expense. This will also provide a more accurate flow analysis. So we'll start a little closer towards the fine mesh, and we'll be running a curvature-based refinement. Let me go ahead and create that. Okay, so compared to the other part, you can see this is definitely much more detailed, much finer mesh. That's good to go. Okay. Okay, now we're going to go specify the material like we did previously. We're going to use just a generic ABS, as previously stated here, some of the material values for it. Looking down into some of these settings, you can adjust some of these depending on your flow analysis and whether you're getting errors such as weld lines or voids. These criteria would be the things you'd want to change to fix some of that. Looking at the melt and the mold temperature, the melt temperature will come pre-specified from the SOLIDWORKS database. The mold temperature you can specify yourself. That will ultimately be reliant on the process capabilities of the injection molder. Continuing down, you can look at injection pressure limits, switch points, and temperature criteria for short shots. Usually when you select your material, most of these will get automatically filled in and if needed, you can come back and adjust these. Lastly, before we run the simulation, we're going to go to our boundary conditions and choose our injection location. As previously stated, ideally the injection location is farthest from the thinnest walls. So we're just going to start off here down at the bottom. Now when we're looking at our actual simulations, with our previous part we just ran a flow simulation. There are two more options, a flow and a pack, a flow pack and a warp. The pack obviously is going to display how the material packs into the mold, and the warp is going to show kind of post-injection how the part is going to fluctuate in size. So we're going to run the flow pack warp. This is going to be much more computationally expensive than just the flow, but we're going to get some more information on the injection.
Okay, so this is the results from our more advanced part. We've already discussed the flow, which you can see here a little bit, but this is what the pack look like, and you can see some of the more advanced analysis that you get out of it. And then something kind of interesting that we ran with the warp here is you can adjust your deformation scale. And so as you increase the scale, it shows you, it just makes the deformation a little bit more obvious. So that allows you to see it a little better. You see it's deformed a little bit up here. So then if we want to look at our flow, we can see the weld lines, which I'll talk about a little bit. You get a weld line when two flows flow together. And so that's kind of why we're getting this these weld lines on these edges here, is because you got flow both from the top and the bottom flowing into that point. And then to discuss our air traps, you can see the air traps here. We get some air traps down here, especially at the sharp edges, because it just gets stuck there, can't flow out easily. So potentially on this model, we can consider adding like a air vent, maybe up here at the top, opposite the direction of flow. And so yeah, that's our flow analysis.